All right, so hopefully this is actually recording, and we'll begin. It is, yeah, good. Now we can begin our PSpice tutorial. So if I go back over to Windows, PSpice, once you download and install it, which by the way is, if we go back over to our web browser, come to this link here, this is where you'll be able to download PSpice. PSpice tutorial. So if you click this, I believe it opens up a pop-up window. You want to scroll down to the bottom of this page and download PSpice 9.1. At least if you're going to use that, this is where I recommend to get it. I guess there's some help files on here. Feel free to browse these. They look like I don't think they were posted there earlier, so I haven't read through them myself. But that's where you want to get it. Again, the tutorial is right here. Definitely recommend looking through this. This will walk you through some of the stuff. We'll take a look at some of those things today on live with PSpice. So after you install PSpice, you'll see it show up here in your Start menu. It'll say PSpice Student, and you can click on that. There's a number of PSpice programs that do various things. The one we want to work with is Capture. That's the one where we can implement schematics and run a simulation of their response. And here's a really important step. So the first time you run this, it's really important not to miss this, is that you right-click on this Capture Student and you want to run it as an administrator. Even if you're logged in on your machine as an administrator, this step has to be done, as I've found and other students in the past have found. It only needs to be done once, the very first time you run it. And if you don't do that, there is one of the essential features of PSpice is not available. And so we want to make sure that you don't do that. So here's the OrCAD Capture environment. You get a session log which reports some details about simulation stats and things like that. Your first time, let's see, in here you want to generate a new project. Yeah? So you can say a new project. The thing to choose is analog or mixed AD. And you can give it a name, so I'll do it Engineering 301 Spring 13. And let's see, I want to browse and put that somewhere. I will put it in, sure, in Engineering 301. I've already created this folder here. And that's fine. Maybe I'll create a directory inside of that. Test 4, sure, why not? Oh, that's not where I meant to put that, but we'll do that. Oh, yeah, that's good. And so we'll say OK. And we want to create a blank project. We'll say, all right. Okay, now we've got a schematic page. This is where you, of course, enter your schematic. And this sort of file system over here shows you some of the important files in your project. We'll take a look at what some of these important folders are in a second. But I recommend leaving that open. And incidentally, this drop-down menu, the one labeled PSpice, is the one that doesn't show up if you fail to run it as an administrator. So things like new simulation, create a netlist, run a simulation, all those things are not available. So very essential features of PSpice. So let's jump into designing a circuit. Now, before we design a circuit, I'd like to take a look at, let's pick a circuit that we want to design and test. So I'm gonna come over here and we can sort of come up with a test circuit. And I'm gonna look at an RC circuit. Since that's a pretty familiar response, or should be from circuit theory, and we can analyze, see if we get the expected results. So if I've got an RC circuit, I'm gonna do something along the lines of, let's say I've got a 10-volt source, and at time t equals 0, a switch is closed. Yeah? And you got your RC, your passive RC circuit here. And this is a value, let's give this a value of 1 kilo ohm. And let's give this a value of 5 nanofarads. All right? And what we're interested in measuring is the response across the capacitor, Vc of t. Okay? So, if we make a plot of Vc of t, what's that look like? The voltage on the cap versus time. How does that look? Concave up, concave down, right? And kind of a logarithmic response, yeah? So something like this. Approaching what value? Right, right. Okay, so approaching 10 volts, right? Great. Now, is there any special time value that I should know about this circuit, right? The time constant, right? And where is that on this graph? Like on the time axis, where is the time constant roughly? 37%? So here 37%. Anyone say anything different? So right here, if this is 30, so here's 37%, yeah? So this would be 10 volts over E. The thing you want to keep in mind is that's for discharging for a voltage. So for charging, it's 63%. All right, so 6.3 volts, about 6.3 volts. When it's reached this value, that is the time constant tau. That's the time that it reaches about 63% of the voltage. And when is that going to happen? How do I find that? Right? It's equal to RC, which is equal to 1 kilo ohm times 5 nanofarads. And what is that? Is it 50? 5 microseconds, right? I think it's 5 microseconds. We'll check. So tau is equal to 5 microseconds. Great. Now how about the current? What if I wanted to plot the current IC of t here? What does that look like? What's it start at? What's it end up at? It ends up at 0. Why?
Because once the voltage is across the capacitor, it's not going to be once it's charged.
Right. Once it's charged, that is the plates on the capacitor are full of charge. They can accept no more, and thus the current drops. When it's fully charged, it acts like an open circuit, right? When it's empty, which it is corresponding to this graph right here, how does it behave? What's its impedance? The cap's impedance. What does the cap behave like when it's not charged at all? A short circuit. That's right. Its impedance is 0. That's exactly right. So if its impedance is 0, and this can be approximated as a wire just connecting right here, then the current should be right 10 volts over 1 kilo ohm. So 10 milliamps, right? Great. So then this should start at 10 milliamps and exponentially decay, or actually kind of logarithmically decay. Or no, I guess exponentially decay down to 0. And this, in this case, this would be this tau now would be around 3.7 milliamps for the discharge. Okay, so we know we've come up with a theory or We've drawn a circuit that we expect to see. We've plotted its response, and we've also kept in mind how many, if this happens at 5 microseconds, we know that the response we want to see is in sort of the 10 microsecond window, 15 microsecond window, something like that, right? This would be 5, 10, and 15, and so on, right? So those are things you want to keep in mind when you're building a simulation to run in PSpice, and we'll see how that influences what we do. All right, so we've done that. Let's go back over to PSpice now, and let's build some circuits. So we're going to place a part. I've got a number of different libraries that I can choose a part from. If these aren't showing for you the first time you run it, you go over to this button here and click Add Library, and then there they are. You can choose analog, breakout, those sorts of things. I've already included them, so they're there for me. Then quickly we'll just design an RC circuit. And so I want, from the analog stuff, I want an R. If I type in the value R and click on it, I'm good to go. There's my R. So I'll say OK. And let me zoom in a little bit here. There we go. That's a little better. And now I'm going to place my capacitor. So here's C. And I believe you can rotate it like so, right? And now I want an input that's going to approximate the step input that I had over here. This portion. Why did that happen? Hello. Oh, whoops. Yeah, this voltage and this switch. That's sort of a step input, yeah? So I want to approximate that with one of PSpice's devices. And the way to do that is to add in you can add in something from the source library. And the one that you want is, and we'll use this a lot, is not just, I think it's V, is it vPulse? It's vPulse, okay? And vPulse lets you define specifically a lot of things about a pulse input. Essentially, you can you have V1 and V2, TD. V1 and V2. V1 is the starting voltage. V2 is the ending voltage, right? TD is the time to delay to turn the step on or to turn the pulse on. TR is the rise time, TF is the fall time, PW is the pulse width, and PER is the period. So just to sort of show what that would look like if you were down here, and then you've got vPulse parameters. So what you have here is if you've got the voltage of the source versus time, and then let's just draw an arbitrary pulse. Okay, so what I've done here is that this is V1, the starting voltage. This is V2, the ending voltage. This time here is TD, the time to delay from the beginning of simulation to turn it on. This is TR, the rise time. This is, of course, the pulse width. And then this is the fall time. And if you wanted this whole thing to be periodic, you can specify a period where, let's say, this were going to occur again. And I believe that's from the starting point. Oh, let me redo that, actually. And this would be the period, PER. Yeah? So those are all the things you can define about this particular pulse source. It gives you a lot of control. So we want a first value of 0 volts. You just type in 0. An ending value of 10. Oops, that's still on V1. An ending value of 10 volts. I'm not going to delay this at all. I'm just going to let it start right when the simulation runs. I'm going to give a rise time of 1 nanosecond. All right, so that sort of gives a very sharp rise, but no step input is infinitely fast. So we'll sort of try to model that a little bit. Fall time I'm not going to worry about because remember I'm just looking at doing a step input. So I don't really care what the fall time is. The pulse width I do care about, and the period I do care about because I want, remember I just want a step input to occur right here, step input of 10 volts. And for it to at least have a pulse width of longer than the time window that I want to view this in, let's say 15 microseconds, and a period much longer than that because I'm not going to really run the simulation any longer than that. So we'll say we'll do a pulse width of of 20 microseconds. Just type in 20U for micro, and a period of, I don't know, 1 second, something. Doesn't really matter. After you have your entire schematic put up here, you can connect them all with wires with the wire tool here. And just connect all these guys. Great. Oops. Okay, we've built the circuit. Really important thing we have to do is define ground. Okay, if you don't define ground, then PSpice doesn't know what its numerical results should be relative to. So you go here and click on this, and let me do that again. You click on this ground symbol here, and you want the ground from CapSim, this one, this just one that says GND, and really important, you have to rename it. For some reason, this has to be renamed to 0, so that PSpice knows that this is numerically equal to 0, that this node is 0 volts. Once you've done that, it can assign a meaningful value to the other node voltages present in the circuit. Right? So now this node is in fact 0 volts. All right. Now that we've done that, you can do something like you can place a probe, a voltage probe here on the capacitor. All right, and that will measure the voltage across the cap when you run a simulation. Let's define a simulation. Well, actually, before we define a simulation, we've just drawn up a circuit inside of PSpice, and we haven't really created any numerical model yet. To do so, you have to create what's called a netlist. Let's do that. Okay, now notice that in this folder, in this outputs folder, I have a .net file. Okay, that's the netlist. It's the numerical representation of my circuit. Let's open it and take a look. So the numerical representation tells you the part value here, the node that is connected to each one of its terminals, starting with terminal 1 and then terminal 2. So one side of R1 is connected to node 9, or net 9, and the other side is connected to net 15. And it has a value of 1 kilo ohm. Same thing with the capacitor, right? Oh, look at that. One of its nodes, its first node is connected to 0. The net 0. That's good. That's good for the numerical model. All right, and then those are the other nodes, and then it tells you what the voltage source is connected to and what its specifications are. Yes? You know what? It was just arbitrarily assigned, and I don't know why it starts with 9 and 15 and not 1 and 2.
Because 0 makes sense as the ground.
0 is the ground, and that makes sense. It doesn't even call it, notice it doesn't even call it net 0. It just calls it 0. It's a special term. It's a special net name that is, you know, representative of 0. So yeah, they start these out with 9 and 15. I would think it would make more sense to start with 1 and 2, but maybe they have their reasons. So, so that's the netlist. Now, keep in mind, this is how PSpice originated. This is what PSpice circuit simulation started out as. Is just typing in stuff in this in a text file like this. So let us all take a moment to really appreciate the advance that's been made in graphical user interfaces, that we get to draw in some circuit like this and compile a numerical model from our drawing. All right. Okay, so we've got a netlist. That's essential. You have to have that before you can create a simulation, or run a simulation at least. Now we can create a simulation. So I'm gonna create a simulation called my first sim, or my test sim. Maybe we'll do like RC time response. That's the name of this simulation. Okay, so I'm going to create it, and now that I've created it, notice it's kind of launching another program that's down here in the bottom window, or it's showing up on as another window opening. All right, so that's part of PSpice being a little bit modular in their programs. And this simulation setting, this is where you want to specify how the simulation runs. First thing is, remember, we're running a time response, right? We want to view the time response here of the voltage versus time, voltage on the cap versus time. So, so time response, or transient, is what we want. You have some other choices like a DC sweep or an AC sweep for doing frequency response, that kind of thing. You'll do those throughout the semester. Very often you'll be doing a transient response, so I think that this is a good example to give. You can choose some options: general settings, Monte Carlo, worst case. You can do a parametric sweep where you adjust the value of one of your components. Well, we're not going to go into that right now, but it's just sort of some of the basics. And here they are. Run to time. This is how long your simulation is going to run. Remember that your simulation is going to give you a graph of its entire runtime. So if we want to see the behavior right around 15 microseconds or so, then we want our runtime to be 15 microseconds. So we set it up. We say 15 U, or 15 mu. That's good. A maximum step size, this sets the resolution of your graph. So if I set it to, I don't know, every 5 microseconds, I wouldn't get a very good graph, right? If I set it to every 5 microseconds, I'd get a point here, a point here, and a point here, right? That would give a pretty choppy graph. That's not what I want. I'd like something much finer than that. So I'm going to set it to, I don't know, 0.1 microseconds. Maybe even, yeah, we'll just try that and see how it goes. If you check this box, I believe that that's used for, and if you're running a simulation where devices have like initial conditions, like initial charge on a capacitor or something like that, I usually just check it and don't worry about it. It seems to be fine. So you apply that stuff, you say okay, that's good, and that's basically all you really needed to do. And once you've done that, now you have the option to run a simulation. You can either click it here or you can click the play button right here. So when I click this, I'll click run. This goes, it launches another PSpice program down here in the bottom, and there's my graph. Excellent. So, were we off in our measurements? No?
Well, maybe.
It looks off to me.
Well, we had a
Is this, oh, that's not right either.
we had a rise time in the PSpice. We had a theoretical rise time of 0.
Right, right. Well, I can show you, if you want to see the step input, and this is a useful thing to look at, we can go over to trace, and you can add a trace, and here's all the net voltages and quantities you can look at. You can look at currents, I through C1, V and stuff. Let's look at V on the supply, V and V1 on the positive side. So I click this one here, and I show that, and now it shows up in red, and you can see the step input is really, really sharp. Right? So regarding our, I thought we predicted that this was going to have a tau of 5 microseconds, and that doesn't seem to be the case. So something went a little funny somewhere. Where is six? This is 6.3 volts here, yeah? I think 2 microseconds. Or 1 microsecond. Huh. Well, something went a little strange there. So here's an instance, a good example of when someone might go back and revise their calculations, like I should do. But to press on with our example, we'll continue. So let's say that that I wanted to add a plot. That instead of just seeing only the voltage here, I wanted to see the current as well. But I wanted to see it not on the same axis setting, but I wanted a whole nother plot down here. It's a useful tool. I recommend trying it out. So you can add a plot. You can add a y-axis. Oh, that's not what I wanted to do, actually. Can I undo that? I can't. Great. Oh, here. This is what I wanted to do. Add plot to window. Now I have a whole other plot. And in this plot, I can add a trace if I want. So let's say I want to add the current through C1, for example. So I click on this. You can also type this stuff in here. By the way, you can also use any of these functions in the right tab over here to operate on these circuit quantities. So if you want the absolute value of something, or the arctangent, or the average, or the log, or something like that, you can just type it in, whatever the thing is, or you can also just click on it, and it'll say log. It puts the cursor here, and then you can do that. Right? So those are useful things. Right now, we just want to compute I through C1, and oh my gosh, what is that? That doesn't look like what we expected to get. How about the values? This is 0 amps. This is minus 10 milliamps. And then asymptotically approaching 0. What do you think happened? Why is the current negative? That's exactly right. The terminals on the schematic, because it all depends on the direction of the current through the cap, right? And so if we go back to the schematic and look at this here, the current is going to register. It's trying to measure what the current is relative from this node going down to this node, since this is 0, right? And as it turns out, if you look at the netlist, the first node in C1 is connected to ground. It always tries to measure the current, or the simulation measures the current relative to the flow from the node 1 to node 2 of the device. So if I, in fact, want the current to show up right, let's just, let's close the simulation here. And then I'm going to, I'm going to delete this stuff. Oh, fine, delete that too. And I'm going to flip the cap around. No, I want to move this whole cap. How do I do that? Okay, that's all right. So, wait, I want to rotate this. Okay, let's just go to place and, I'm sorry, edit and rotate. And rotate again. All right, so I've flipped it around 180 degrees. We'll wire it back up. And then run the simulation again. But before we run the simulation again, we need to do what? Got to add the probe. That's true. So I put the probe on here. That's good. What else do I need to do? The simulation is already specified. That's already defined. What's changed? The net list, or rather, the circuit has changed. We need a new net list to reflect this, right? So after we've done this, then you just need to create net list. Great. It's re-rendered, and you open it up, and notice now C1, the first node is connected to, now it's named 55. How about that? And the second node is connected to ground. Just do me a favor and plug that in real quick. Thank you. Okay. So, so now that we've run that, or compiled a new netlist, we can run the simulation. This shows up here. Great, we get the same voltage graph. If I wanted, I can add a plot to the window. Come over here, add a trace, add the current, and hit OK, and there we get the expected response. It starts out at 10 milliamps and asymptotically approaches 0.
That probe you put allows you to get the current and voltage. So there's no such thing as just the current.
There is a current probe actually, and let's try and run it like that. Let's come over here, and if we take a current probe and we place it right on the device, right on C1, it doesn't matter which side you put it on. I don't think it does. And then now I run my simulation. I don't think you have to render the netlist for placing probes down. So I say run, I go over here, both the probes lit up, notice, and I come over here, and see, that's kind of what I don't like about that, is that the voltage scale, whatever takes up the larger unit scale, dominates the response graph. There's lots of data happening here, but it is unobservable because it's so small. It's 1,000 times smaller, right? So that's why I usually, for current and voltage, I try to just put them on their own thing. You can also add a y-axis like we did here, and I think that if you somehow you can set this to render the currents value. I don't exactly remember how to do that, but now there are cursors, right? So if you wanted to tools, no, that's not what I want. Oh, here you go, cursors, and display some cursors. You can now move this cursor along here, right? And the probe cursor tells you the resolution. Now, if I'm trying to estimate, let's say this 6.3 thing here. Notice the best I can get is 6.352. So what I want to hint at is that you're starting to get some sense of error show up here, and you want to try and assess that reading from PSpice. Try and see what your measurement resolution is. Okay. All right. So that's pretty much the PSpice tutorial I had to give. I'm going to close this stuff up here and go back over to, I'm going to close this, close that, and end our recording.